Hey there, AppSec engineers. Welcome to another video in the application security series. In this video, we'll be talking about SQL injection in Node.js applications. In October 2024, a critical SQL injection vulnerability was discovered in Pandora FMS, a popular software for monitoring computer networks. The vulnerability, tracked as CVE 2024-9987, was a post-authentication SQL injection vulnerability within the filters parameter of the extension's functionality. This allowed attackers to execute arbitrary SQL commands on the underlying database server with system privileges. SQL injection occurs when an application builds database queries by concatenating user inputs directly into SQL statements. So, much like other injection attacks, you will notice that the problem really starts by sourcing user inputs directly. In Node.js applications, this often happens when developers prioritize rapid development over security. And usually, this happens in the form of string concatenation instead of thoroughly and well-built parameterization. The immediate impact of something like this could be that data breaches can result in significant financial loss. And did you know that the average cost of a SQL injection attack exceeds $196,000? Further, if personal data were exposed, regulatory fines could reach millions of dollars. But more technically, this could result in unauthorized access to user credentials, data manipulation or even destruction, and system-level access in severe cases. Let's switch to our hands-on labs for an example application. We will look at both the attack and the defense segment in this video. Before diving into the attack, let us start by looking at the vulnerable code. In this example application, we have a very simplistic marks card viewing system. And you will notice that what we're doing here is serving an express application on the marks endpoint, where the expectation is that the user inputs an ID, a student ID in this case, to retrieve their marks. You will notice on line 34 that we're concatenating the ID that we source from the user request directly into the SQL query. Further, there is no input validation, there is no parameterization, and further, the error, if there were one, is directly fed back as a response. In the sense, we have error messages that are overly informative. Let's take a look at this in action. Like I said, this is a simplistic application that is expecting the user to supply their ID. So for example, if I were to give the roll number 12, I will see a name, an age, and some marks. If I were to go back and say 11, I get roll number 11's information. However, if I were to try and input a number that would not exist, it tells me exactly what does not exist in the database. And further, we realize that it is simply a string that is being pushed back to us. Let us see if we can exploit this in some interesting way. Because we understand that this is a simple case of string reflection, we can try an injection payload. This is the very well-known 1 equals to 1 command, which is always going to be true. What you'll see here is that we're giving it a negative number, but the single quote here ends the ID value and continues the SQL statement with an OR operator. And you will notice that 1 equals to 1 is always going to be true. And voila, we are met with every single user in this database. Let us take a look at all the user data that is available within this database. While what we're seeing is only student ID, name, age, and their marks, as well as their pass or fail status, there also seems to be an address variable, and more importantly, there is also all the hashes of their passwords. So let's see if we can write a SQL query that can dump this information. Let me show you what I've crafted. In this case, I have a valid ID, but then I'm performing a union select to ensure that I have the student's username and their password being dumped from the student login table. And because I'm using my good old 1 equals to 1 trick, it'll always be true. You'll notice that this time, not only do I have the roll number, their name, but I also have their username and password, the hash of their password in this case. But with this data, I could potentially use rainbow tables to try and break this hash as well. The key takeaway here is that this user, in this case, a student, is not supposed to be able to view their username and password through this portal. But through SQL injection, they're able to dump all of that information onto this page. Luckily for us, the defense in this case is also equally easy. And because SQL injection has existed as a flaw for several years already, there exist techniques that are very easy to leverage, two of which are using parameterized statements and using ORMs that are well known to guard against such problems. Let's go ahead and implement parameterization in this case. As we've noticed that the problem was on line number 34, where we are concatenating the string directly, let's go ahead and replace that portion with a better way of doing things. You will notice that the only difference here really is that instead of concatenating a string like so, I'm using a special character, which is a placeholder for a parameter. In this case, I'm using a placeholder question mark, which tells the database driver that I'm expecting a parameter here, and the parameter is going to be completely separated from the query itself. Further, we can also implement a degree of input validation by expecting only digits to be entered in our request field. We can also enhance our errors by ensuring that they're not as leaky, and instead of dumping the entire error into the response, we could respond with a more generic response. For now, let's go ahead and use only parameterization to see how it'll work. With the application running again, let's try our previous tricks. To begin with, let us see if the application is working as intended. And we see that it is. Let's see if we can retrieve negative values. We still get the same overly informative error message, but is it vulnerable? It seems not. This is possible because parameterization completely separates the user input from the SQL query itself. And therefore, because they never mingle, injection probabilities are entirely reduced. Heck, they're removed. As with any injection flaws, never trust any user input. And using parameterized queries is just so simple and easy that you can always find the version that will work with your language and with your database and with your implementation. To go further, input validation is always your first door of defense. Implement it right and implement it first. Lastly, but not least importantly, it is quite important that your database is running with the appropriate privileges. If your database user, in this case the application user that is accessing the database, has root privileges or has excessive permissions than required, then your attack surface and therefore the data or the information that they can draw from this database also increases exponentially. As always, use the principle of least privileges for anything. Hope you learned something, and I will see you in the next one.